Okay, well, first of all, I'd like to thank the organizers for letting me speak here. And again, I would like to thank them for actually inventing and creating this seminar. I think it's a great opportunity for people to present their work. And I will speak today about the dynamical phase transition of ASEP in the KPZ regime. So this is basically what I would like to understand are shocks of ASEP in the KPZ regime. So speaking to a rather specialized audience, I think I can be relatively brief about introducing the ASEP, but just to fix some notation. So we are looking at the asymmetric simple exclusion process on the integers, and particles have independent exponential 1 clocks. And whenever that clock rings, a particle tries to increase its position by 1 with probability p, which is bigger than 1/2, and it decreases its position by -1 with probability 1 minus p, which we call q. Okay, however, there's an exclusion constraint. So as you see here in this illustration, if a particle tries to jump to a position that is occupied by another particle, then that jump is simply suppressed. Okay, so the Spade space of this continuous time Markov process, that's just all maps from the integers to the set 0, 1, where we think of the ones as particles and of the zeros as holes. Okay, and if nu is a measure on the state space, we call nu st the distribution of the ASEP with initial measure nu. Okay, so this is the ASEP. Now, ASEP has a very well developed hydrodynamic theory, and I will briefly summarize this. So if you consider a sequence of ASEP initial configurations, eta n, and you call eta tn the state of the ASEP at time t, which was started from the configuration eta n, then the following holds. So if you fix two real numbers a and b is bigger than a, then if you assume that there's a nice initial density or u0, meaning that if the number of particles that eta n has in the interval a and bn, if that divided by n converges to the integral of some initial density function u0, then you also know that for later macroscopic times, this empirical density will converge to something. Namely, if you look at the number of particles of eta tau n in the interval a and bn, and you divide that by n, this will then converge to the integral from a to b of a function u dot tau, where this function u x tau, that is the entropy solution of the Burgers equation. So it is the Burgers equation which governs the large time particle density of the ASEP. And so this Burgers equation is a PDE, and one way you can solve this is using the method of characteristics. Okay, so maybe I just say a few words about this. So the idea is that you have your PDE with some initial data u0, and then you want to construct lines along which the solution of the PDE is constant. And what I've illustrated here is one example. So here on the left, you see u0, which has density 1 on all the negative integers. And whenever the density is 1, the characteristic lines are just lines with slope 1 over the strength of the asymmetry, so 1 over p minus q. Okay, and initially to the right of the origin, the density is 0, and whenever the density is 0, you have characteristic lines with constant slope 1 over the strength of the asymmetry. So here it's -1 over the strength of the asymmetry. But then you have this area here, this rarefaction fan, where a priori it's not clear what's actually going on, but what turns out to be true is that for the entropy solution of the Burgers equation, what happens is that the characteristics are fibrate inside this rarefaction fan. So going from slope -1 over P minus Q, it goes continuously to the line which has slope 1 over P minus Q. And what this means in terms of the particle density is that if you look at the solution of the Burgers equation at macroscopic time 1, you will see the so-called rarefaction fan, which is just a region where the density continuously goes from 1 to 0. Okay. Now, this was a case where initially you had a discontinuity in the particle density, but this discontinuity disappears immediately in the Burgers equation. However, you can also have discontinuities in the Burgers equation which survive for all times. And these are called shocks. Okay? And here you see an example. So basically, what you see here is that I have two rarefaction fans. So in red are the characteristic lines of two rarefaction fans. So I have one rarefaction fan here and another rarefaction fan here. And the initial density is such that from the origin up to the point P minus Q, the density is 1. So you have characteristics with slope -1 over P minus Q. And from the position minus P minus Q up to the origin, the density is 0. So you have characteristic lines with slope 1 over P minus Q. And then what you see is that if you look at the macroscopic time tau equals to 1, this is this horizontal line here, then after that macroscopic time, the characteristics from the rarefaction fan will come together. Okay, so before the macroscopic time tau equals to 1, you had here a shock wave. But however, what happened at the shock is that just the characteristics from the density 0 and the density 1 region came together. But after the macroscopic time tau equals to 1, it is the characteristics which from the rarefaction fans which will come together. And so what this means is that if you look after the macroscopic time 1, then actually the information coming from the two rarefaction fans they will interact with each other. Before, if you look at tau smaller than 1, these two rarefaction fans do not interact with each other. They do not see each other. Okay? And this thick black line here is the shock wave, which in this example has 0 speed. Okay? I hope this is clear. Now, what we will be interested in is we want to understand what is happening at this shock on a microscopic level. So we want to know what particles do at this shock. And we will actually put ourselves in a critical time regime where we precisely transit from the time point tau equals to 1 to the regime where tau is strictly bigger than 1. Okay, so we will transit from the regime where the two fans do not interact to the regime where they do interact with each other. Okay. So here on the last slide, I showed you the characteristics. Here I show you the corresponding initial density. So here on the left, you see the initial density U0. And the initial density is simply that you have density 1 up to the position minus P minus Q. Then you have density 0, a region of density 0. And then you again have a region of density 1 going from the origin up to position P minus Q. And then if you look at the large time density of the Burgers equation at macroscopic time 1, what you see is that you have two rarefaction fans which just come together. So you have this left-hand rarefaction fan, which really ends at the origin, and you have another rarefaction fan which starts at the origin. And the density here is 1. Okay? And in terms of, initial configuration, a sequence of initial configuration, which creates you this left-hand density that can be constructed as follows. So you look at the sequence eta n, which is defined as follows. So here on the left, you have the indicator functions consisting of all integers which are smaller than minus n times p minus q. Okay, so that means you have density 1 to the left of minus p minus q. And then you add that to that, you add the indicator function of the discrete interval going from the origin to the point n times p minus q, which means that you have density 1 in between the origin and p minus q. And the fact that we're interested in a critical time regime where we transit from tau equals to 1 to tau strictly bigger than 1, this will be realized by looking at the following time. So this is what you see here. So, oops. So we will be looking at this, the ASEP at the following time. We'll look at the time n plus a critical parameter, which is 2 times square root of m divided by square root of p minus q times square root of n. And this parameter m here, that is our scaling parameter, which is independent of m. So if m is 0, we really look at the macroscopic time tau equals 1. However, if we send m to infinity, this corresponds to transit into the region where tau is strictly bigger than 1. Okay? So to summarize this, so if you want to transit from the macroscopic time 1 to the macroscopic time which is strictly bigger than 1, what we will actually consider is we'll consider the double limit t going to first goes time to infinity and then goes m to infinity. Okay, I hope this critical scaling has become clear. Yeah. So again, here you see on top you see the initial configuration eta n that we consider, and here's again the critical time that we're interested in. Okay, so but now I can solve this simple equation for n, and you get that n is the same as t minus square root of t times my scaling factor plus an order 1 term. Now I can plug this in, this value for n. I can plug this in the definition of eta n, and then this gives an alternative description of the initial configuration, namely we have the following initial configuration. So we have everything is full of particles up to a certain position. And that position is minus p minus q times t minus square root of t times the scaling parameter square root of m. And then there's a scaling factor 2 over square root of divided by square root of p minus q. Okay, so and in these black dots here, these are the particles. And then you have a region of folds, which goes until the origin. And then you have yet another region of particles, which goes from the origin again to the point p minus q times t minus square root of m times square root of t times 2 divided by square root of p minus q. And in this rewriting, I hope it kind of maybe becomes clearer what this parameter m actually does. So you see here that here's a minus sign in front. So if m gets bigger and bigger, what this means is that these group of particles come closer and closer to the origin. So, and if this group of particles comes closer and closer to the origin, there will be more particles which actually reach the origin. So if you increase m, this increases the density of particles directly to the left of the shock. And if you increase m on the right-hand side, what this means is that these group of holes comes closer and closer to the origin. So more holes arrive at the origin, and this decreases the density of the rarefaction fan to the right of the shock. Okay?
Sorry, I have a question.
Yeah.
So Is there a reason like we consider this n to the 1/2 regime?
Oh, yeah. I mean, I hope it will become clear later. It just turns out, so this square root of n regime is related to the fact that if you have, say, ASEP with step initial data, and you look at the particle number m, where m does not grow with t, then this particle still has a 1/2 fluctuation exponent.
Ah, okay, I see. Thanks.
Yeah. Okay. So this is the initial data we're interested in. And just a few remarks. So what is important in this shock is that there's no initial randomness. So what we expect to see is some kind of KBZ-like behavior if we look at the double limit, first time going to infinity and then m going to infinity. And I mean, these shocks in ASEP have been thoroughly studied in the 90s and beyond. However, it was always random initial data which were covered. And for these random initial data, various results were obtained. They proved limit results for the second-class particle. They obtained the so-called dynamical phase transition. And one purpose of this project is to show that in this critical regime that we have here, there are actually KPZ relatives of these results for random initial data. And what happens is that the Gaussian, which is present in the random initial data, that has to be replaced by the tracy with a GUE-distribution. Okay. Okay, so now we'll state the results. So, one moment, exactly. So here I call delta eta 0 t the Dirac measure on our sequence of initial data eta 0 t. Okay, so the initial data that I had just defined. And then I need to define the shift operator. So given an configuration eta, we define the shift operator sigma z of eta, which is just the configuration eta shifted by the integer z. Okay? And the shift operator naturally extends not only to configurations, but to measures on configurations. Okay? So now we introduce a notation we call P of xi. P of xi equals the probability that the difference of two independent GUE-distributed random variables is smaller or equal than xi. Okay, so you have two independent GUEs, you look at their difference, and you look at the probability that this difference is smaller than xi. And here's the first result, which is so-called dynamical phase transition for ASEP. So if you take xi and r, and you look at the distribution of the ASEP at time t when started from our initial configuration, and then you first send time to infinity, and then you send m to infinity, and then you shift your measure on the KPZ scale, so m to the power 1/3 times xi. This limiting measure is given as a convex combination of the following two measures. So it is given as 1 minus p of xi times μ0, which is the Dirac measure on the configurations which has no particles, plus p of xi times μ1, where μ1 is the Dirac measure which has of the configuration which has no holes. Okay? And this is called a dynamical phase transition because the limit law is not a single distribution, but it's a convex combinations of two other distributions. And I mean, this μ0 and this μ1, these can be seen as kind of degenerate examples of the Bernoulli product measures, μ rho, So in general, for rho between 0 and 1, you can define an invariant measure nu rho, where the occupation variables of your ASEP are IID Bernoulli rho distributed. Okay, and if you set rho equal to 0 and 1, you recover exactly these Dirac measures. Okay.
Sorry. So
yeah.
If you only have the rarefaction fin like on one side, then like will your C becomes only the trace rhythm GUE instead of like the difference of them?
Oh yeah. Oh yeah. Oh yeah. Okay, yeah. That is exactly correct. So
okay.
If you would have if you would have density 1 on the whole of R plus, and then you would have a one-sided chalk, and you would only get a single GUE. Yes.
I see. Thanks.
Yeah. Okay. So now this limiting result here, this should be understood through the lens of second-class particles. So, but before I come to that, just one simple remark. If I set psi equals to 0, so I do not shift at all, then the limit law is just 1/2 times nu0 plus 1/2 times nu1, simply because pi of 0 is 1/2. Okay. Okay, so what this means is that if psi becomes very big, and I look at a position m to the power 1/3 times psi, then what I will see is all I will see are just particles. Okay, and likewise, if I then look at position minus m to the power 1/3 times xi, all I will see are holes. Okay, simply because if psi goes to plus infinity, then pi of psi goes to 1. P of psi goes to 1. Okay. And to explain a bit this result, we look at second-class particles. Namely, what we will see is that this P of psi, so the probability of that 2 independent GUEs are smaller than psi, that is exactly the probability that a second-class particle, which was initially placed at the origin, remains to the left of the position m to the power 1/3 times psi. Okay. So here you see kind of a pictorial representation. So I take the exact same initial data as before. However, I do change one thing, namely, I replace the normal particle, which was initially at the origin, by a second-class particle, which is here depicted in red. Okay. And just to remind you, so the second-class particle, it interacts with holes like a particle and with particles like a hole. So if a particle jumps to the position of a second-class particle, then they exchange positions. And if the second-class particle jumps to the position of a first-class particle, nothing happens. And if the second-class particle jumps to the position of a hole, then they exchange positions. Okay. Now we denote by x of t the position of the second-class particle at time t. Okay. And now we can prove a central limit theorem for this second-class particle. So what we have is that if I look at the second-class particle, its position x of t, I rescale this position by m to the power 1/3, and I look at the probability that this remains to the left of some real number psi, then in this double limit, this gives me exactly P of psi, so the P above. Okay. So basically, the second-class particle is telling you where the density 1 region is and where the density 0 region is. And coming back to the characteristic lines I'd shown you in the beginning, then there's there's a lot of evidence, or you can actually should see these second-class particles as microscopic versions of the characteristic lines of the Berg's equation. So just, for example, if you have a rarefaction fan and you put initially a second-class particle at the edge of the rarefaction fan, then what the second-class particle will do is it will choose uniformly and random one of the characteristics which start from the rarefaction fan and follow that characteristics. And if you place a second-class particle at the shock, just like we do here, then the second-class particle will also follow the shock wave. Okay? So I won't give any kind of detailed proofs, but I just would like to kind of give a heuristic understanding of these two results. So in order to understand these two results, it's actually helpful to consider ASEP with a much, much simpler shock. Okay, and just how can one create a much, much simpler shock? That you can do actually, or maybe I should switch to the next slide actually. Exactly, yeah. So one very well-known invariant measure of the ASEP is the so-called product blocking measure. So the product blocking measure is a product measure, and I call it mu, and the probability that mu has a particle at a given position I, so the probability that mu assigns to the configurations which have a particle at I, that is precisely given by p over q to the power I divided by 1 plus p over q to the power I. And if you send I to plus infinity, you see that this quotient goes to 1. If you send I to minus infinity, you see that this quotient goes to 0. Okay, so yeah, so for mu, it becomes the density of particles becomes 1 if you go to the right, and it becomes 0 if you go to the left. And this mu is actually supported on a countable union of sets, each of which is again countable. So this mu lives on the union of spaces omega z, where these omega z consists of all the configurations zeta, such that the number of particles of zeta to the left of z equals the number of holes of zeta to the right or at position z, and these two numbers are finite. Okay? And then we call mu z, we call mu z is just a product blocking measure conditioned to live on omega z. Okay, and these mu z's are again then invariant measures for ASEP. Okay, and I mean the hydrodynamic profile of these blocking measures is relatively trivial. So it's just for all macroscopic times tau, the density is just 1 to the right of the origin. Okay, there's nothing special going on here. And however, now we will look at second-class particles in this very simple shock. So if you now take an initial configuration zeta, which belongs to such a space omega z here, and now you start ASEP from such an element in omega z, together with a second-class particle. So pictorially it looks like this. So one element of the space omega z is, for example, the configurations which has everything full to the right of position z. Yeah. So here everything is just full, and then everything to the left of z is just empty. But somewhere there's a second-class particle. It doesn't matter where it is initially. Okay. And if I denote by xzt the position of the second-class particle at time t, then it's not very difficult to compute the limiting law of that second-class particle. And what you get the following result. So the probability that this second-class particle here is at position I, this converges as t goes to infinity to another probability, which is the probability that a certain random variable v0 plus z equals this integer I. So, and now what is this random variable v0? v0 is an explicit random variable, a z-valued random variable, and its distribution is given as follows. So the probability that v0 equals some integer j, that is given by the difference, by a certain difference, namely the difference of the probability that the measure mu0 has a particle at position j plus 1 minus the probability that the measure mu0 has a particle at j. Okay? So this is the limiting behavior of the second-class particle in this very, very simple case. So if t is large, we can informally, what we can informally write from this convergence here is that for if t is large, then the second-class particle xz of t approximately is v0, this random variable v0, plus z. Okay? Now what we would like to understand is, we would like to understand our shock as kind of a departure from this very simple situation. So if we come back to our problem, we have the following initial configuration eta 0 t. So we have a second-class particle at the origin, and then, however, here we have this infinite region of particles. Then we have this finite region of holes. Then we have this finite region of particles. And then we have this finite region of holes. And compared to the simple situation of a configuration which lives in omega z, so there are two mechanisms. So what doesn't happen in omega z, but what happens here is that you have this group of particles which will travel to the right, and once they interact with the second-class particle, they will pull the second-class particle to the left. Okay, that is one mechanism. The other mechanism is that now you have this group of holes here, which travel to the left, and once they interact with the second-class particle, they will pull the second-class particle to the right. Okay? And now we call this green p here, we call the green p, that should be the random number of particles that reach the second-class particle up to time t. So these are the particles which I underlined here in green. So from this infinite group of particles, there will be a random number of particles which up to time t has actually reached the origin and has interacted with the second-class particle. Likewise, we call this blue h here, that we call the random number of holes from this infinite group of holes which reach the second-class particle up to time t. Okay? And I call the leftmost particle from this group which has reached the origin, that I call xp, and the rightmost hole from this region here which reached the second-class particle, that I call hh. Okay? And now the idea that we have is that once this particle xp and this hole hh have reached the second-class particle, there are no new particles and no new holes which arrive and which interact with the second-class particle. So what I should be able to do is, I should be able to do is that once the p particles and these h holes have interacted with the second-class particle, I should be able to replace all particles which are to the left of the particle xp by holes, and I should be able to replace all holes which are to the right of position hh by particles, and this replacement should not change the behavior of the second-class particle. At least that is the idea, because P and H are precisely defined in such a way that they are the particles and holes which are relevant for the second class particle. Okay. Now, if I do that, what happens? So if I do that replacement, I get a configuration, I get a particle configuration which lies in the random state space omega H minus P. Okay. But now for deterministic indices of omega, we saw that we know everything about the second class particle. So motivated by the result that we have for this very simple shock, what we might hope to be true is that this xt equals actually H minus P plus this random variable V0. Okay, that is just at this stage is just a hope. But now, if somehow we can make sense of what is written here, if we can somehow say in a precise way that x of t really is approximately H minus P plus V0, then if we first make sense of this the statement, and if we then show that H and P are asymptotically independent and asymptotically GUE distributed, then we would have the CLT for the second class particle, right? Because if H and P turn out to be asymptotically independent and GUE distributed, then the difference of H and P will be distributed as the difference of two independent GUE distributions. Okay. And however, I mean, this, you should be very skeptical about this, what is written here. I mean, in order to justify this this sign, I mean, I used a result which was for where I was state in a deterministic state space, and I was sending time to infinity. Now I'm in the random state space, and the time parameter also goes to infinity. However, the initial data also depends on time. So one of the things that you have to make sure to make this here precise is you have to make sure that regardless of what H and P actually are, you still have enough time to mix to this equilibrium. Okay, that's one of the problems you have when you want to show that. And the other thing is that you have to show that H and P are asymptotically independent. And just for, let me just mention for the experts, one technology that you have to use in order to show that is the so-called Lee decorrelation method. Okay. So this was the heuristics for the second class particle. Now, how can we understand the dynamical phase transition? So for the dynamical phase transition, let me call PLR the probability, the limiting probability of the event that H equals some integer R and P equals some integer L. Okay. And actually, you can show that since H and P decouple asymptotically, this limit is actually the same as the limit of the product of H being R times the probability that P equals L. Okay, so in this limit, these two things are actually already decoupled. Okay, but in mind, so PLR is the probability that H equals R and P equals L. And the idea now is that if the event H equals R and P equals L happens, then the ASEP at time t should be distributed like the distribution mu with index R minus L, right? Because there are R holes coming to the origin and there are L particles coming to the origin. And then if you do that as replacement, you precisely obtain a configuration which lies in the space omega R minus L, And if you are able to show that there's actually enough time for this configuration to come close to equilibrium, then you obtain that your ASEP will be distributed like this measure mu r minus L. Okay? And this intuition turns out to be true. So if you look at the limiting distribution of this ASEP when time goes to infinity, this is going to be distributed as an infinite linear combination of these condition product blocking measures. So it's going to be distributed as the sum over all non-negative integers r and l of PLR times the condition product blocking measure mu r minus L. Okay? So what this means is that with probability PLR, I kind of pick the state space omega r minus L. And once you have this limiting result, then it's actually not too hard to obtain the double limit results where you now have to send m to plus infinity. One of the key things that you have to do in order to extract the dynamical phase transition is that what you have to show is that this blue H and this green P, that each one of them converges to the Tracy-Widom GUE-distribution. Okay? And for that, you have to compare the ASEP that you have with the ASEP with step initial data, for which we know that particles converge to the Tracy-Widom GUE-distribution. Okay? Just to finish, I would just like to make a remark. So in spirit, these two results that I showed you should be compared to the earlier results by notably Ferrari and Fontes for shocks which are created by random initial configurations. So if you look at the initial measure nu lambda rho, which means that your initial occupation variables are independent and they are Bernoulli lambda distributed on the negative integers, and they are Bernoulli rho distributed on the non-negative integers, and you assume that lambda is strictly positive and it's strictly smaller than rho, and then what you then see is that there's a shock which moves with speed. Oh, let me write that down actually. So there's a shock with speed p minus q times 1 minus lambda minus rho. And then you can again put a second class particle at this shock. And I call this second class particle, I call x lambda rho. And just to state in words what was shown for that by Ferrari and Fontes, that it's again true that x lambda rho is determined by a random difference of particles and holes. However, the randomness of the number of holes and the number of particles in this case does not come from the ASEP dynamics, but it's the random number of particles and holes which are present initially in a fixed segment. Okay, so each one of these random number of holes is going to be a sum of IID Bernoullis, and hence by the central limit theorem, each one of these numbers of holes and particles will converge to a Gaussian. Okay, and then the second class particle will converge in distribution to the difference of these two Gaussians, which are independent, and hence this difference is again a Gaussian. Okay, so in that case, what happens to x lambda r is that the limit law is distributed like a Gaussian, and you can also for this random initial data, you can also obtain a dynamical phase transition where then the limit law is a convex combination of the Bernoulli lambda distribution and the Bernoulli rho distribution. And then what replaces the P of psi, so the probability that two independent GUEs are smaller than psi, this gets precisely replaced by the probability that two independent Gaussians are smaller than psi. Okay? And I'm actually already finished.
Well, okay, thank you very much, Peter. So let's see if somebody has some questions.
Peter, a short question. You had nu0, nu rho, no, nu0, nu1, just because they just touch. If
Yes.
the technique would hold, you would have nu lambda or nu 1 minus lambda from.
Yes, yes. So yes, exactly. So if if you wait, let me write this down. So if you had a shock where so if you had another shock where things look like that, where so if you had such a shock where here the density is positive and then that's positive, okay, and then maybe call this here say rho1, this rho2, then what I strongly suggest is that then you would have nu rho1 times p psi plus nu rho2 of p of psi, 1 minus p of psi, sorry. Yeah. Oops. So it should be 1 minus p of psi times nu rho1 times this times p of psi. So that is what is to be expected. But I think that not even for ASEP this is known. For TASEP this is known.
Should you go from like the single limit to double limit? Do you want to have like, do you need to have like some rate of convergence for this single limit or something?
No, actually no, because I mean in this case you can actually explicitly compute the t to infinity limit, both for the second class particle and for the limiting distribution. So you don't need kind of any bounds on how fast the convergence to t happens. But however, to get to that t to infinity convergence, you do need these bounds on the mixing times, which actually tell you that close to the origin you are in equilibrium.
I see. Thanks.
So your heuristic argument somehow reminded me of the recent paper by Nejjar and Sassamoto, where they proved some sort of confirmation of nonlinear fluctuating hydrodynamics. And they also found that for another model, so a full exchange of particles, the probability of this full exchange gives a product of a GUE and of a, well, depends on a normal distribution. So is it related?
Oh, okay, so no, I haven't looked into that paper, so I wouldn't know.
So in any case, so is there any, well, is there any like argument that relates this distribution of the shock with some nonlinear fluctuating hydrodynamics?
I wouldn't know. It would be interesting, but I wouldn't know. It's a good question. Yeah, no, I'm not sure. But I'll definitely look into this this paper.
In any case, the techniques that it seems that you use, they do not necessarily go to Bethe ansatz or any integrability, right?
No, it's very probabilistic in that sense. So I mean, I use as input that ASEP with step initial data has been solved, and then everything is probabilistic. So I show that xt is asymptotically equal to this difference of h and p, and from that you get the limit law for x of t, and you can get the limiting distribution of the ASEP. Yeah. So I mean, yeah. So I think there's recent work by Patrick Ferrari and Alexei Buvetov where they look at TASEP, and there they use different techniques for the second-class particle. They use color position symmetry. So that is a technique which very much relates on explicit formulas.
Is it possible to use a color position symmetry for ASEP in any way?
Yeah, I mean, the method itself is not restricted to TASEP at all, but I mean, so far it seems quite difficult to do, but yeah. But a priori, there's no reason that it should not be working. Are there other questions or something?
Let's see if there are other comments.
I had a quick question, actually.
Mm-hmm.
Yeah, sure.
Can you say anything about this ASEP? I guess it would have to be ASEP maybe in the diffusive scaling.
So you mean about, what do you mean? You mean the random initial data, or what do you mean?
So I guess any initial data in principle, but if you take something with like weak asymmetry, but then you look at time n squared. So maybe
okay.
the scaling of the KPZ equation or something.
Yeah, yeah, I mean, I would love to do that, but yeah, I mean, I have not managed so far to do that, but it would be, I think, would be very interesting to see how these shock fluctuations, how they, or if they survive this weakly asymmetric scaling. But yeah, I don't know.
Well, okay. Let's wait maybe a few minutes more.
Yeah.
If,
I will stick around just in case somebody wants to ask something.
So let me just, because I'm very, I don't know, let me just post the paper I was talking about to the chat.
Ah, okay.
And so there is, so the relation I see is that it's just because there are two GUE that come as a limiting result. So I thought it was I don't know.
So I don't know exactly. That paper I did not look at, but I saw some talk of Jan before.
Mm-hmm.
So I know this is 8. I know this paper 8. I thought you said recent, so it was, I saw 2000. Okay. Now then is the paper that where Jan he was speaking about.
Yeah, I think
essentially the idea is that, so if you look in terms of the right basis in the, what is called, there are two modes. There is a system with different particles. So if you look in the right mode, they essentially behave independently.
Mm-hmm.
So intuitively, you would think that if you look in the right mode, at least before we made also something in a related model where it was, we made some numerics, and indeed you would see that if you look in the two natural mode, where then they kind of, stuff crosses without seeing each other. At least numerically was clear. And what happens there, if you look in the right mode, there are two KPs in mode. When you look in, if they exchange, then the probability they look, they should correspond to a difference of two stuff.
So also in this case, T and H, they correspond to.
It's not the same problem, but intuitively, physically, you expect to have the result. There is no proof for that, of course, but
yeah, because the heuristic result that I showed, it's completely the same as for the total exchange in the AHR mode.
Yes. There is some analogy in the heuristic, but the problem is different. But
for example, in the AHR, one can, modifying the initial condition, one can obtain, I don't know, maybe a product of a GOE.
Mm-hmm.
Would it be possible also in this case? So assume that you have the theorem that said that the flat ASEP obeys to GOE.
Yeah. So I mean, yes. Assume that what you would expect is that if you, instead of looking at the second class particle at the shock, if you look at the tagged particle at the shock, this should have exactly this product structure. And I mean, I did not talk about it. So in the shock that I showed you, it's also shown that the tagged particle at the shock will converge to a product of two GUEs.
So also for the Bike-Rein's the law, you can recover a theorem, including the Bike-Rein distribution, for example.
So I mean, on the shock level, I mean, so you want to have where you want to have a product of a Bike-Reins and something else?
Yeah, maybe GU. No, I'm trying to see if this heuristic argument, how far you can go with it. So
Bike-Reins you will not get.
Yeah.
Bike-Reins is when you're stationary, but if you have two stationary, in the shock you see only the randomness of the initial condition.
Yeah.
But in principle, you could do, if you have density rho 1 but non-random density rho 2, you might be able to do something similar. But the difficulty is what Peter already said, that the statement that is visible now for rho 1 strictly positive and rho 2 strictly less than Z1 is not proven.
Yeah.
But I think if you prove this for the generic one for GUE, probably you can also do for GOE, I guess. I don't know the detail.
Yeah. Yeah, I mean, in this flat case, I mean, there are these GUE times GUE results by Patrick and myself, but they are very much the way they are proved. They are very much restricted to ASEP, because we use the coupling to less passage percolation. So.
In principle, what we made, you can also do in the space-time picture, but there are some input which are missing from integrable solvable problem. So we had some input from integrability that in the generic ASEP, you don't have all the inputs, so that we use. But physically, there is no real difference, but mathematically, yes.
Yes.